All right, so together, Max and myself are going to spend the next, 50 minutes or so, going through some outlines, some trends that we see going on in electronics generally. We're going to give you some insight into what we see our customers are doing, give you some insights to how successful they're being, etc., some of the challenges they're facing. We're also going to cover some of the key areas that they're looking into, some of the engineering disciplines and some of the specific elements they're doing as well. We're also going to cover some of the capabilities that we have as well. So Max and I are going to take you through, well, actually specifically Max is going to take you through a demonstration of some of the more critical areas that we think are important, a great example of where we think simulation can add some value, and then couple up some other good advice along the way, some best practices, if you will, that we think we've seen. Hopefully that makes some sense. Max, did you think I missed anything? We got anything to add there?
No, I think it's good.
Awesome. So we get on with this then. So hopefully you can see my screen change. Let's make sure that's all working. So when we look at electronics, there's something rather special going on with electronics versus other industries, right? There's no doubt in my mind that electronics and the things that people can do with electronics is really driving some fundamental shifts in a variety of different industries, right? The idea of smart is in just about every industry that we can name, and electronics is an increasingly critical part of what people do. No surprise there. But we also see some trends within electronics and the intersection of what goes on with electronics and software and hardware as well, right? Increasingly, the big obvious one is this drive from hardware to software. Increasingly, hardware-driven systems and processes become circuits and circuit boards, ultimately being combined with software into integrated circuits, and ultimately just a pure software play in and of itself. So obviously this ingests or creates a really high degree of flexibility with customers as they start to inject these things into their systems and into their products and into their designs. All of a sudden, it becomes immediately possible to make a change to the way something behaves. So the benefits that can be had from this process are really quite fantastic, right? Shouldn't be a surprise, therefore, that our customers have all sorts of different initiatives and drives to try and incorporate these elements into their designs. Digitization, mobility, IoT, automation, electrification. These are all great examples of initiatives we see day in, day out amongst our customers. So it's important to be able to realize what this value can bring and be able to incorporate some of these ideas into what we do in order to predict how designs and performance works. So no great surprise then that with all of these initiatives that a little bit of a revolution is underway, right? So, if you look at some interesting research we have from Deloitte and Tech Clarity, we can see that a lot of manufacturers out there, the vast majority of manufacturers, are doing something around digitization or aspects thereof. In fact, only 8% of manufacturers believe that current businesses are going to remain viable if their industry continues to digitize, so that they've got to change. What's more is that the vast majority of manufacturers are doing something. You can see this final statistic on the right-hand side. 84% of manufacturers are delivering, researching, or considering digitally transformed offerings. So this is a big shift we're looking at here. Now, from our perspective, the interesting thing is that few manufacturers really feel prepared for this, right? A lot of them are really trying to figure out how they can become part of what's increasingly being known as this fourth industrial revolution, right? I'm sure many of these trends are obvious to you, that many of you know these things, right? The pressure that customers are seeing when we look at them is all the different processes, all the different ways in which these different groups involved in this process need to work. We see more traditional processes like stage gate or phase gate, particularly in the mechanical world. Then we look at the software world at the other end of the spectrum with things like continuous integration and developing, where the system and the process, the software is always on and they're continually updating it live. So bridging these gaps is quite a challenge. Getting people to work in this environment is difficult. From our perspective, this process that we're talking about, this new product introduction process, is really quite critical. We believe that simulation plays a unique role. when you look at how many products actually make it, not just to market, but successful in the marketplace for electronics, it's a relatively small proportion. Very few of them actually are that successful. Only 3% actually make it to the shelf. And then when they do get there, they don't particularly work out too well. So there's a key question that simulation for us plays in this world, right? At the end of the day, we've got to figure out whether our new technology is going to work in the new products that we're introducing to market, that we're manufacturing, in many cases in their millions. So it's an important question. Simulation clearly does something. So what is it that people are doing? So we start looking at our customers. Now, we're very fortunate at MSC to have some of the world's leading customers in the electronic space. And we've been looking at those, Max, myself, and the rest, various other members of the team, to understand what some of them are doing. You know, we look at the guys providing electronic components. So the likes of Sumitomo, a great example, or Omron, or some of these other guys, right? Great examples. You know, we take a nice example here from Muzatani, right? They want environmentally friendly heatsink designs. So straight off the bat, you're looking at new materials, straight away, right? And we've got to manage the compliance of those materials, obviously. And if it's going to be environmentally friendly, then it's got to do its job well. It's got to be efficient. In this case, not only getting rid of heat from the electronics themselves, but also in the material in and of itself. Things like recycling become important. So it's important to minimize these things, get them efficient as possible. So there's a unique combination here of new materials, thermal characteristics, strength characteristics going on. So we believe that obviously simulation is a key part of this process. You know, these sort of examples are mirrored with others, right? In this particular case, we're looking at the most common form of failure for electronic components is the stress caused by heating up and cooling down, switching on and switching off. In this particular case, one of our thermal solutions, SE Stream, coupled with structural simulation. So we can start to simulate the thermostructural stresses going on in the components. We take a slightly broader viewpoint. We start looking at the guys doing the electronics and the mechatronics systems that use these things. Now, a really nice example, just get this movie playing, we have here's from one of our customers here in Europe, Analog Way. In this particular case, this piece of equipment is powering the highest resolution video display in the history of Times Square. So you can imagine on Times Square, that is a very public and very visible place. If this goes down, people will immediately notice. So the people running this video display needed to be reliable, they needed to work, obviously. In this particular case, we're not only simulating the thermal characteristics of it, as well as potentially some of the structural characteristics of it, but perhaps just as importantly, some of the environmental considerations that go around it. Simply put, is it going to get wet? Is wet going to get in it? Is there going to be dust? All sorts of characteristics being included in the simulation here for these guys. Again, another interesting example. In this particular case, the world's first holographic augmented reality navigation system. So obviously this has got to sit in the car, and you can see from the screenshot here, it's projecting things onto the windscreen of the driver. So if this particular component gets too hot, that laser that projects onto the windscreen, that's going to start not working too well. That's going to have a fairly large impact on something that needs to work consistently and reliably, not just for people getting around, but also some safety aspects in here. So again, cooling efficiency becomes important. But in this case, being able to optimize a design to specifically meet thermal considerations is also important. So we're leveraging the design to match the physics that we need to be able to deliver. Some obvious things so far, right? Another great example, which I'm actually really impressed by, a company called Tentec here. In this particular case, they're taking that idea of, let's say, reliability and robust design to the next level up. In this particular case, we're talking about electronics in avionics. So you can imagine, pretty important stuff, right? Lives are at risk when this goes bad. You can also see from this screenshot that in addition to simulating the thermal characteristics of these particular piece of equipment, they're doing a whole bunch of additional simulation. We'll talk about a little bit about some of those later. But you can also see rather practical insights that they're getting with that kind of donut-shaped element at the back, right? Being able to tell where the heat is going and where it's coming from quantitatively and clearly is an important element here. Some practical tools that we're looking for from an electronic simulation. We'll talk a little bit about that shortly. Also, a really nice example we have from one of our customers here, well-known photocopier printer manufacturer. In this particular case, using a combination of elements together. Right, so obviously as the paper goes through these things, ink and toner being attracted to the paper ultimately is a really unique combination of motion, thermal, fluid, design variations going on here as well, not to mention electronics, electrostatics going on here as well. So fairly high degree of variation and obviously an extremely complicated design here. You can see in here the level of detail in this particular model is, it's really quite extraordinary. So somehow we also have to be able to bring in the models and deal with them. So then taking the next level up again, right? That's where we see some core performance at the end of the product need to be outlined. So we see that with a number of our customers, right? So Panasonic being an interesting one here with the electronics that they provide, not just to the end consumer. In fact, if you look here, you can see on the right there a camcorder, for example. You can also see some solutions for the household in terms of smart offerings, appliances, and automotive and industrial systems. So a whole range of places where we can consider applying these things. Taking some of those ideas, you look at one of our favorite customers, Yamaha, taking a step further with acoustic simulation. So being able to, in this case, predict the sounds that comes from these speakers. It goes a lot further. Yamaha don't just make speakers. You take a simple example, perhaps of an exhaust on a motorbike. All of a sudden, we're simulating a wide variety of phenomena in as much as an accurate way as we can. The phenomena that really matter. For me, nothing speaks more clearly to that than one of our customers, Bose, right? These guys have a fantastic reputation for sound quality, and we're very proud to count them as a customer here at MSC. In this particular case, you saw some of the things that we're doing with acoustic simulation, enabled to manage this effectively to meet customers' increasing ideas of what performance means. So that end result, that focus becomes critically important. So a wide variety of considerations that we see our customers doing. Right? From materials modeling, which I mentioned straight at the start, electronic component design, enclosure design, acoustics, noise, cooling, mechatronics systems design, packaging, and even the manufacturing process. We'll talk about some of these in a little bit more depth. And so we look at materials, right? So we're not just talking about, putting material properties into a simulation here. We're talking about fundamentally simulating the way a material is going to behave. We look at tools like that we have with Digimet, for example. We can start to do that. We can start to understand how materials are going to behave, compare them to experimental results, and start predicting the structural, thermal, electrical characteristics. And obviously, that's important from a prediction point of view for the material itself. But when you start combining that with management capabilities, all of a sudden, we've got a very powerful tool for compliance, which is really fantastic, right? A lot of these electronic pieces, that's a really important consideration. We then look at the next level up, right? Components and the things that are made from these materials, right? Whether it's something as simple as a twisted piece of wire or a crimped connector, for example, you can see there on the top, or as simple as a fan or something like a Peltier device or a heat sink. Some of these things are important to be able to simulate to understand the overall component performance simulation, even to the point of how we place something on a board. You can see that example on the bottom right there with a bit of chip and solder simulation, even right up through to the PCB and the thermal characteristics in it. Speaking of the PCB, once these components are on a board in some way, it's also important at that level too. Whether it's something as perhaps obvious as structural integrity, here you can see a flexible board vibrating there, or whether it's the thermal performance from the PCB and the layers within it and the components on it, or even the thermostructural example that I mentioned before. These elements can be important, and depending where you are in the supply chain, these things are going to be things you perhaps need to consider. Then, of course, as we take the next level up, the bringing together of these things into a system, right? With in this case, the enclosure, right? So here simulating thermostructural loading again, but increasingly more what I might call higher level performance attributes. Things like vibration, crack, fatigue, failures, that kind of thing. A great example of this is drop test, right? So if any of you have ever dropped your phone, as I unfortunately did a few days ago, this sort of thing becomes important. In my case, I was fortunate. My phone, whilst it did get a scratch, it didn't smash to pieces, somewhat as a result of simulation like this. Right, where we can start to see how the components interact, we can start to understand the best place to put fasteners, and in my case, perhaps, where we need a cover for the phone. So then we get to cooling. Now, for us, this is a big deal, right? The cooling of the electronics. There's a couple of examples I mentioned earlier. This is increasingly important, but I'm not just talking about a CFD perspective, which is what a lot of people talk about here. Somehow we need to be able to combine a total view of the simulation. Right, so whether that's conduction or convection, so thermal and CFD coming together, or whether it's including some electrical effects like Joule effect, for example, or even chemical reactions. We need to be able to bring these things together to provide a thorough viewpoint from a thermal perspective of what's going on, not least including many of the environmental elements that go around it. Things like particles, for example, become important. So a really neat example taken a step above that in the realm of mechatronics is Panasonic here in the top right. What you're actually looking at there is the world's smallest optical disk drive. Now, in this particular case, that's what you're looking at there is some simulation from Cradle to simulate thermofluid performance here. But as you can imagine, this is the world's smallest optical disk drive. So in order to make that disk drive work, Panasonic had to invest in new materials for many of the components in it. They had to invest in new control systems to enable the disk drive to work, in addition to being able to measure the thermal reaction of the parts, be able to understand how the different parts interact, and as well as things like dust. Really, really important. Another good example with Eaton here. Molar switchgear, part of Eaton, innovative leader in some of the solutions that are used thereof. In this particular case, we're using atoms to study detailed switchgear performance. You can see on the top left there as well, great example of somewhere where mechatronics is really, precision mechatronics is really important. In this particular case, you can see that's a lens. It's got a mechatronic system to help control how the different lenses react to each other. So when you need that performance, it's there. We've already mentioned acoustics, right? A key part of what we do, particularly for an end user. The idea of quality is largely affected by these. So even though where acoustics is important in the obvious cases like this, with a phone or some earbuds, it really does make a difference. But you also see this in other areas as well, right? I mentioned a great example with Yamaha earlier with the acoustic simulation of an exhaust, for example. There's other cases here too. And then, of course, manufacturing, right? So increasingly, we've been growing out, we've been seeing a lot of examples here as we start to simulate the manufacturing process, clamping, crimping. In this case, you can see progressive die going on. You can see the connectors being formed up, the enclosures being formed up, right? Being able to accurately predict how these things behave on the production line is going to largely dictate how things behave in reality out there in the real world. So manufacturing process simulation is a key part of what we do. A great example here was some connectors on top of a well-known battery provider, right? These things are critical. To make them work in their perhaps even billions is a big, big challenge and a key part of an MPI process. Getting that throughputs and yield is a key part of what we see. One of the extreme areas where we see this happening is with wafer manufacturing. Again, we've got a couple of examples here, Hirata and Nikon, where on each wafer there are, a huge amount of individual integrated circuits. And when you start producing these at scale, the accuracy and fidelity of these models really, really gets important. In these cases with the manufacturing process, that's what you're looking at. If you're not aware of how ICs are manufacturing, that's actually the machine that does a lot of the manufacturing process. We're looking at the manufacturing of the wafers themselves. So pretty accurate stuff. And then, of course, ultimately, when you look at manufacturing processes, particularly for electronics, they're very sensitive. So even beyond the manufacturing process itself, there is the manufacturing environment in which these things are manufactured. Right? Particularly, as you can see here from one of our customers, a very key part of the process to get this right. If you talk to the likes of Intel or and other manufacturers of integrated circuits, this is a key part of what they do. It has to be clean. The sorts of size of the models dictate that it must be. So some interesting elements. At the end of the day, we talked about the new product introduction process, though. In order for that to work, we need to somehow connect the guys coming up with the new technologies, the new ideas, the new materials. We need to connect what they're doing to the design and engineering guys, the guys who are going to utilize these new technologies in the products they develop. We're going to have to take those new technologies and morph them to a point where we can make the designs that we want to deliver to market work. And ultimately, these guys need to be connected to manufacturing. At the end of the day, there's no point designing something if you can't actually make it. So we need to be able to make them, in some cases in their millions. So tools like Sim Manager or whatever the management tool set that goes around these people starts to become key. In order for make this process work, tools like this are critical, because the success of many MPI introductions is based on how well these three groups can get together to deliver what the customers actually need. So really critical. So enough of me, enough of the presentation. Max, if you're still there, how about we show an example of what we can do in some of these areas? Sound reasonable?
Yeah, for sure. So please just give me the hand.
Hopefully you have that now.
Yeah, here we go. So let's start with the PCB level. So maybe in your project at the early stage, you know that on your PCB you will have several components that will dissipate heat, and maybe you're worrying about it, about the thermal behavior of it. So at this early stage, we have tools to help you about this. In a very simple way, you can just describe the layout of your PCB in a very simple way. For sure, if you have already some existing files, such as IDF files, you can also import it here. So here I have my PCB. I can also give some information about its environment, regarding especially the ambient temperature. We can also consider an hypothetic housing around it, a very simple one. And then we can also deal with this specific component that make us worry about the thermal behavior. So just describe in a very simple way this component regarding the amount of heat that will be dissipated. Let's say, for example, this kind of behavior for thermal consideration. So let's pretend we have more than just one component. For example, like this. Okay. Okay, here we go. So we have our PCB with the main component that will dissipate heat. And at this early stage, within few seconds, as you can see, you can get some results about the expected thermal behavior of them. And the very interesting point about this, it's really in live, it's dynamic. And with this, you can test a lot of different configuration to check the best location maybe for your components, to be sure that the thermal behavior won't be a problem further in the project. You can also test maybe the layout of your PCB with several layers here. You can also test, for example, the benefit of putting some thermal vias beneath the components. So this is at the early stage, just on the PCB level. And once you have done so far these few simulations, you can also send it to a more standard CFD tool that will allow you to also consider the mechanical environment of your electronic card. So for that, we'll use another tool here that will allow you to also take into account the CAD data, the mechanical CAD data around your system. So here we start with a small wizard that will help us to quickly set the outlines of the simulation. So in this case, we just have to point here on the CAD data that we want to use in this case. So we have several kinds of format that we can use. neutral files, but also native files from Mechanical CAD software. Of course, in this case, we'll be interested by the model itself, as you can see here as a preview in the background. But since we are dealing with thermal consideration, maybe it could be also worth to consider the external air of it. So let's just consider a volume of air surrounding our system, like this. We can also choose the kind of physics that we want to be taken into account in the calculation. We can also set an ambient temperature, and then choose between different configurations. Is your system open to the air? Is it included in another housing, maybe not modelized here, exposed to a strong airflow, sorry, maybe pulsed by a fan, for example. And at this point, you have imported your system in the GUI of the software, and you have also quickly set the main outline of the simulation. So here we have a system here, and we will consider a volume of air around it. And maybe you can also specify, for example, if specific volumes will dissipate some calories. So for example, here on this PCB, maybe this specific component will dissipate some calories. So you can apply on it specific material properties. So let's say, for example, it's made of copper, and it also generates some heat. So in this very simple way, you can describe the way each component here will behave in your system. And if you have, for example, more complex systems such as fans, heat pipes, and so on, we have a full set of modelization that can help you to handle it in a very simple way to get faster calculation. And from this, you can now consider meshing it. So for meshing, we can set the size of the mesh cells that we want to use, but we can also set here the level of detail that we want to be kept after the mesh. So it means that with this parameter, you're allowed to make CAD data cleaning easily, because from this, if you consider this specific example, this CAD data directly come from GrabCAD, for example, and we can go straight to the mesh. We don't need any CAD data simplification. So as you can guess, it can save a lot of time. I have an example in mind with one of our biggest customers in Japan. I think it was something like an assembly made of 30,000 parts. So I can let you imagine if you have to make manual CAD data cleaning, it can be very big waste of time. So here the good point is that you don't need this boring stage, because you can handle it directly within the mesh step. So this is for the setting up of the simulation, and then you just have to run the simulation so that you get your results. And in the post-treatment, you are able to check the result that you get with this specific configuration. So as you can see here, we can, for example, check the temperature level on the system itself. So we can deal also with the CAD around it if needed. So you can check the temperature themselves. You can also check the way the airflow will behave. So in this case, just to have an idea about its behavior here. But for us, this is just a status, but this is not the end. At this point, you just get the status about the thermal distribution of your system when it's working. But if you want to go further, we can also use this kind of tools that Keith mentioned previously to help you to get an insight about the thermal behavior of your system. For example, here, if we are considering the housing of this specific system, you can see here from the housing that the heat will come, for the half part of it, will come from convection, for maybe 20% from radiation, and the rest for other parts by conduction. So it helps you to quantify the different contributions of the surrounding of your system, but also the different components of your system about the thermal dissipation. And as you can see here, the main part of the heat that will be released by the housing directly go to the convection. So it means maybe that it's not worth to spend time on the surface of the housing, because radiation here is not a big deal for releasing heat transfer. So this is when you want to check part by part or assembly by assembly, but you can also get a global picture of it. So here we get a global vision of all the parts of your system. So don't worry, you can also manage this in a smarter way. So let's focus on the biggest heat transfer within the system. So here, with this specific picture, you can get a very quick idea about the heat transfer within the system, because here the red arrows stands for the heat coming from one part to the other, and their size are proportional to the amount of heat exchange between these parts. So as you can see here, the component tops are the main provider of heat within the system, and the main part of it will go from the component to the heatsink, the first heatsink, and will be released to the air. But you can also notice here, I have a second heatsink in my model. So this graphic card is made of two main heatsinks, and we can quantify from this picture that maybe the second heatsink is not mandatory, because if you just consider the amount of heat that will pass through this second heatsink, it can be neglectable. So from this, you can get your conclusion, your first conclusion about your first try. Maybe you can go back to your CAD system or here our tool Apex. So Apex is a convenient tool, a very easy to use software, so that, for example, simulation guy can also deal with their own CAD modification on their own. So you don't need to go back to the CAD genius to make this modification. So on this, maybe you will make modifications. So for example, on the housing, and maybe you just want to make some openings in it to facilitate the airflow. And then from this, you just have to go back here in your simulation model. Maybe just replace the part that will be changed. So in this case, the housing. Just import the new one. That's it. Here we saw that the second heatsink is not mandatory, so just let's delete it. We can remesh the system. So as you can see here, in few seconds, I get 3 million elements. So it's not a big deal for us to create a mesh, even for poor quality CAD. And from this, you are able to rerun your calculation. And of course, you are also able to compare directly the results you get from both simulations to be sure that you are improving your design in the right way. So this is for the software themselves. So Keith, I will give you the hand here.
Thanks, Max. So hopefully you can see my screen again, Max.
Yeah, we can.
Excellent. Right, so as we went through that workflow, there's a couple of big ideas there that I think are important. Frankly, not just for electronics, I might add. So Max started off with some fairly simple design tools, design simulation, right there at the front of the process. Being able to quickly address, even in a simple way, what might happen and start to assess different examples like Max did there, just simply dragging things around and getting a real-time result. You know, I don't care what you're using or how you're doing it, that's important because you can get some immediate feedback and get rid of the silly ideas before they've got any traction. Get rid of the rubbish ideas quickly, and then you can focus on the ones that do matter. What also is important there, Max did it when he went to the more complex example. We need a way at the end of the day to bring MCAD and ECAD together in one place without a lot of fuss. You know, just a simple pull down there what Max showed you. You know, whatever the tool set is, being able to bring in MCAD data and the ECAD data into a single place to simulate, so it's kind of a given. It's needed. And Max also, I think, hit something that's really quite important, particularly with these large simulations we're talking about. 30,000 components, did you say, Max? If that's the one I'm thinking of, that's a 500 million size CFD analysis. It's pretty big, right? And you can imagine the CAD that goes along with that. Having to mess around with CAD is not a value-added time. So if you are looking at tools like this, being able to get to the problems that you're looking at without futzing about with questionable CAD and view the results that you need is really important. What we want are people spending time in that post-processing area, the area where you can get the results that you need and start to interpret them. So again, if you're looking for solutions, being able to pragmatically understand those results is desperately important, right? That tool that Max showed you, the showing the heat path, is really pragmatic, right? And you don't need to be an expert in CFD to figure out what's going on. In fact, you don't even need a CAD of the CFD to figure out what's going on. We can share those particular files and that viewer to every design engineer. Very, very simple way of interpreting and interrogating results. Really powerful, right? Then practically, the idea of making a change, right? So a lot of people talk about associativity, which actually in my experience is overburdensome. But the idea of being able to simply re-import something and hit the update button is important. And then being able, obviously, to compare what happened before versus what happened now is paramount, right? Obviously. So these are some practical ideas that for us are critical when considering workflow for these tool sets, whatever system you're looking at, whatever process you're looking at. You know, there's some other elements that we feel are important for getting started as well, right? The most fundamental one is being able to focus on the problems that you need, right? And it sounds kind of obvious, but often we're engineers and we like to solve problems. And sometimes we get a bit carried away with things that don't matter. Being able to focus on the key elements of performance is important. Whether it's as simple as starting with something like a design simulation tool right at the start of the process to help you focus, or more advanced tools later on to validate what you're doing, being able to focus on what matters to you and your customers and the designs that they're creating is really, really important. So how do you do that, right? Simple question, right? How do you know if you fixed a particular problem, it's going to have the effect that you want? You know, you've got to start thinking about these basic questions. Right? What sort of insight do you need? And frankly, so what? If you fix it, will it make a difference? Right? So key questions before you go anywhere near anybody's simulation tool sets or even into the design process itself. Needless to say that we also touched on some other key elements throughout this process as well. The people, right? These, for me, are the most important part of the process, not the tools. Right, so whether you're an R&D guy wanting to evaluate a new material or understand the impact of the mix of new materials so that you can start to predict its performance, or understand a new technology introduction, being able to evaluate different options, more options faster, and gain that insight is really important. And then being able to connect to the design and engineering teams so that they can take those great ideas, put them in the designs that are going to work and really unlock the value of that new technology so that we can focus at the end of the day on what the customer's looking for. So we can optimize that performance. And then ultimately, those guys, well, three of them need to be connected as well to manufacturing. As I said earlier, if you're going to create 1 million of them, it's really important that A, they work, but B, they actually meet the needs of the customer, and then finally, that you can actually make them. So being able to drive throughput, improve yield, drive quality is really important. And enabling these guys to work together is desperately important, desperately key, which is why we showed a workflow, right? This workflow was a simple design simulation that might go from R&D through to design. We didn't, in this case, go through to manufacturing. But considering the workflows that are important to your products and your designs is obviously second to none. Being able to optimize and, in many cases, automate these processes is really important, particularly when you understand some of the key metrics involved. One of our customers, Sony, is a great example of automating the process, right? They did an analysis of what their design engineers and engineers were doing, and they found that 40% of their time was spent really trying to figure out how to use a product or a process and not actually interrogating results. So they needed a way to improve that 40%. They wanted to change that to a much higher figure. So the way they did it was embedding their standard processes into a lot of automation so that the guys could spend less time trying to figure out how the software worked and more time evaluating different iterations. Real simple example. Now, at the end of the day, we are a software company, so I cannot talk about the technology. Of course, it is an important part of it. In many cases, like guys, we have a bit of a challenge, right? So all these different tool sets, sometimes, often as not, are buried deep into different individual disciplines. And of course, as your needs change through the life cycle of your design, it becomes you need different tools at different points, right? I touched on some good examples earlier, right? In for the evaluation of new materials, right? That might be for you more a case of doing that in R&D, which is where you might need that insight. Well, maybe in the manufacturing space, it's less impactful to have that, and maybe more impactful to understand how our different parts are going to snap together. So somehow, some way, as your design, as your life cycle changes here, you need to be able to get at the different tools as you need them. In addition, now I don't know about you, but I've noticed that when I want to understand how things work, unfortunately, it's not just in one domain, right? And we all know that many software companies have these different one domains that work together. So increasingly, it's important to be able to get at the tools you need when you need them and be able to focus on them, and in many cases, connect them together as well. So all of a sudden, you really need to be able to get access to what you need when you need it. If you're considering a vendor, a provider, I think this is one, from our perspective, a selfish one perhaps, one of the most important things you can consider. Does your vendor allow you to get at the tools you need when you need them, not when the sales guy or the support guy is ready to answer your call? From our perspective, we're quite proud that we have something called MSC One, which allows people to do that. Simply put, MSC One is a token-based system, and it's based on the idea of usage. So when you use one of our many tools, it takes from the token set a set amount of tokens, and when you're finished with that tool set, it puts them back. You can install the software as many times as you like. So that, with a set amount of tokens, allows you as customers to get access to the tools when you need them. It's really as simple as that. Another important area is that we figure that partnering is an important idea, right? Especially when there's all these different disciplines that you might need to consider. Now, as a software vendor, any software vendor will typically point to 3 different areas at least. If they're good, there's one in particular they'll focus on. Right? There's the basic training, of course, that every product has, usually included within the software. It's in the box. Now, the great news about that is there's training included. The bad news about that, take my Sony example, you don't get paid to learn how to use new software. You get paid to design things or simulate things. So it's not a great use of your time. On the other end of the spectrum, the simulation services. Now, like many, MSC also provides simulation services. Now, the challenge here, of course, is that you get some great results, but you don't often get the intellectual property that comes with them. So that's an important consideration, right? So while vendors can do the work for us, you've got to wonder if it's the best thing for you. What I prefer, what we found many of our customers prefer, is something called a jumpstart. Here, we work with our customers on a real use case, often before they've purchased the software. We work with them to identify their specific use case that they need to get solved, and we work with them to solve that use case. Usually, we spend a couple of days showing them where the basic buttons are, and then at least that final day, we'll take their geometry, their problem, their challenge, and work with them to get a specific answer to that problem. We'll get it documented, we'll have results for you. And then we provide a couple of other days to support over a trial period, maybe a month or so, and then make sure that our customers are doing the work that they need. That's fantastic, right? That's a bit different from normally what most companies do, which is sell you the software and then give you access to training. At the end of a jumpstart, for example, if a company's not doing this, I think this is the best way forward. You'll have some real results on a real use case. You'll have tested the software as well. You'll have some experience if you didn't have it already, and you get some real insight, right? So from our perspective, we talk about this a lot with our customers. A good company will be able to partner with you on that sort of footing so that you can leverage their experience, right? So, being honest, you guys have all the world's experience in electronics, electronic component design, etc. But we have a lot of experience and breadth dealing with customers too. So somehow being able to marry those together is really, really important, whichever partner you choose to pick. So from our perspective here at MSC Software, we believe that we've got a whole variety of very good things that we can offer to customers. We've got some of the world's most trusted simulation and support tools. Right? Our average renewal rate is 95%. Our customer satisfaction, therefore, is high. We've got some very practical tools, right? The example that Max showed you, that CFD tool set, 3 days and we'll have you doing your use case. That's pretty good. That's practical. The insight you need to drive your design, right? Well, a great example there. 30,000 components, right? Meshed without, well, actually, Max, any that I saw CAD preparation, right? Straight from the CAD, straight into a solution, right?
Yeah, that's it.
And then, I've given you some examples here where we've got not just a range of simulation tools, but an ability to couple them together as well, right? Tremendously important, particularly as your design processes change and morph throughout the life cycle of a product's progression. So pretty important ideas, all available ultimately in an MSC One toolset. We think we've got something quite special for electronic components providers, electronic manufacturers generally. That's why we put this offer out there, right? An offer to get involved in a real project, something real, right? Not a benchmark, not some esoteric theoretical example, but some real cases, some real problems that you're facing. So if you're on the call, you're interested, we'll throw that offer out to you to get involved with us on a real project. We think that jumpstart is a great way to get engaged with what you're doing. If you want to get involved, there's a polling questionnaire that should have popped up on your screen, or you can email me keith.perrin@mscsoftware.com, or Yijian, or even Max. You can get in touch with us, and we'll see how we can do on your real projects.